Well, welcome to Blue Pen Land here. Evidently, dropping magnets through coils or suspending them with a spring so that they bounce up and down is something that happens a lot in IB land. At least there's a lot of questions about that. So let's take a look at this. So this is a data logger. This is going to read the voltage across it. We drop the magnet in there. Notice that there's like a reverse potential and then there's a positive potential. And the reason for that is that if let's say this is the North Pole approaching, right? As this thing approaches, the current's going to flow in this coil so that this side facing the magnet is a North Pole and that's a South Pole, okay? And so the current is going to flow this way. So evidently this is the negative side of this thing and that's the positive side, right? Because we get a reverse potential. And when current flows into the negative lead, then you get a negative voltage like that. Okay, so we get a negative one, then we get a positive one, and that's because, of course, the battery is going away, and now there's a South Pole there and a North Pole there, and the current will change on this coil so that that's a North Pole and that's a South Pole. Because in both cases, you want to either repel the approaching magnet or attract the receding magnet, okay? Because you're always trying to prevent the magnet from doing what it's doing. Or another way to think about it is that the movement of this magnet, some of its kinetic energy, it's not on the spring now, right? Some of its kinetic energy is turning into electrical energy, okay? So that means that there must be a resistive force acting against it, okay? So anyway, that's what's going on here. Now notice that this peak is higher, okay? We'll do this in class, or we'll have done this in class, right? You understand that the reason that the approaching peak is lower and the receding peak is higher is that the magnet, by the time it gets down here, is going faster. Okay, so higher is faster. Okay, so let's take a look at the first question. I think we've answered some of the first question, right? So explain with reference to Faraday and Lenz's laws, right? So Faraday's law, we need to refer to Faraday's law, and that is that the EMF is I don't even know if the number of windings is part of it, right? But it's negative n, and then it's the rate change of flux, right? So d flux, they have deltas, right? We can just say d dt like this, right? Okay, so when you change the flux, as a magnet moves, it changes the magnetic field over time. There's a rate change of that, and that induces a current. Lenz's law says that it opposes either the change in flux or the motion of the magnet. Okay, so explain the shape of the graph, right? Well, initially, the North Pole is approaching the top of the coil, so the current flows in one direction, right? So that the top is north and the bottom is south. That's the first picture, right? As it approaches, it's going to go this way, and that yields this negative potential here, right? And then at the end, we've got the same thing, right? And now the magnet is receding from the coil, right? And there's the north and there's the south, right? And the current's going to flow in this coil to prevent it from receding. So that's going to make a north on the bottom and a south on the top. And that makes the current flow the other way, right? The fact that the first peak is shorter is that it's going slower here than it is going here because it's accelerating through there, right? Okay. So Lenz's law is that the current flows to oppose, that's an E, either the change in flux, you can argue that, or the motion of the magnet. Okay, technically I think Lenz's law is the change in flux, but a more concrete argument is the motion of the magnet. Okay, and then the coil has 1500 turns, so that's N, right? Okay, so E is, we're going to kind of ignore that minus sign there. And then it's d flux dt, right? And what they're trying to find, what they're having you find is this. That is the rate change of flux, right? So this is really pretty easy. The maximum will be the maximum voltage. So read that off the graph. Number of windings is 1500. Put that in for there. and then solve for the thing in the parentheses. We're not solving for time or the flux. We're solving for the rate change of flux, right? Now, what units is flux in? Well, remember, flux is BA cos theta, right? Cos theta has no units, so it's B times A. So that is Tesla is B, right? And then meters squared, which is actually a Weber. That's 1 Weber. Okay, a Weber. And a Weber per square meter is a Tesla. It's kind of crazy. It's hard to picture more than 1 Weber in a square meter, but there it is. Okay, I've known a few Webers over the years, so it's hard to picture that. But anyway, there you go. You'll get not a very big change. It's on the order of 10 to the minus fourth. Okay. Okay, let's go look at the next page here. Okay. The magnet is now suspended from a spring. Okay, so there it is, right? And the magnet now oscillates up and down. Let's see, a sinusoidal alternating current with an RMS value of 280 nanoamps is induced in the coil. State in words, notice I say words, so don't be giving them a formula, how the RMS value of the alternating current relates to a direct current, okay? What you need to say here is that it has to do with the power, okay? This direct current, a direct current of 280 nanoamps delivers the same power as an RMS current. That's the real meaning of RMS. It's a power average, okay? All right, so let's take a look at this guy. The coil has a resistance of 150 mega ohms. So 1.5 million ohms. 1.5 times 10 to the 6th ohms. That's our resistance, right? Calculate the peak voltage. Well, let's first figure out the peak current, right? So find I naught, right? And then V is just going to be I naught R. Okay, how do you find I naught? Well, 280, isn't it IRMS? Is I naught divided by the square root of 2, right? So this is what they're saying is the RMS, right? So solve. So it's going to be this number times the square root of 2, right? Okay, and then multiply that. Notice that that's nanoamps. Nanoamps is 280 times 10 to the minus 9th amps, right? Okay, so let's get our metric prefixes there correct. Plug that in there, you're going to get more current, right? And then multiply by the resistance. And you get a number that's between 0.5 and 1 volts, okay? Okay, explain what effect the generation of current has on the oscillation of the magnet. Well, at 280 nanoamps, right, the actual magnetic attraction and repulsion of this thing is fairly inconsequential compared to like the air friction. I'm just guessing, and this is just a guess. But I think what they want us to say here is that remember that as the magnet approaches, let's say the bottom's north and the top's south. They don't even tell us that, right? But if the bottom is north and the top is south, okay, as the magnet approaches, the current flows to oppose that motion. It's always being opposed. Okay, so the current is always going to flow to oppose the motion of the magnet. This will tend to slow the magnet down. You can make an energy argument too, right? This thing has kinetic and potential energy. It's got the simple harmonic oscillator has energy, but that energy is going into this coil, right? Okay. Really, they should have like a resistor here and then put the data logger across that because anyway. But yeah, it would go into ultimately and turn into heat. Right, so it's turning the kinetic energy, the kinetic and potential energy of the simple harmonic oscillator into heat. I'm going to just stop talking. I think that's it for this guy, right?